Hello everybody, in this video we're going to take what we've learned about gravity and apply it to some pretty useful concepts. We're going to talk about surface gravity, orbital velocity, and escape velocity. Now these are going to be some pretty math intensive subjects. I'm going to try my best to be very clear about what you need to know and how you need to work problems in this class for homeworks, quizzes, and exams, so you can have a better understanding that I'm not going to be demanding crazy derivations and equation solving out of you. And I also want to motivate this video because the subject material we're going to talk about is the stuff that sci-fi writers, video game producers, things like that, they dream of and they have to work with when they create these imaginary worlds that are realistic. It's also the stuff of how we operate in space. This is going to be our rocket science lecture in short. Because if we want to put something in orbit, we need to be able to calculate its orbital velocity. If we want to launch something that is going to go to Mars, we need to launch it with a minimum of the escape velocity. This is going to be all the background stuff to understand how we actually go about exploring our solar system and maybe eventually going out of our solar system and exploring the stars. So, really important stuff with lots of applications. Just go ask the people at SpaceX, go ask the people at NASA, and they will all know about these topics pretty intimately. All right, so let's go ahead and dive in and share with you some of the cooler applications of what we're going to learn in Unit 1, Part 3. All right, so let's start with what surface gravity is. This is a bit of a misnomer. Because whenever we talk about surface gravity, we're talking about an acceleration, not gravity. We're talking about the acceleration that we feel on Earth due to gravity, or the acceleration if we were on the moon, that the moon's gravity puts on us. So notice that whenever we talk about the units of surface gravity, it's going to be an acceleration, meters per second squared. Now, I want to go ahead and talk through this slide. I know there are a bunch of equations up here, but just going to connect a couple of ideas. To show why we went through Newton's laws of motion, why we went through Newton's universal law of gravity. We're going to put those ideas together to really see why Newton needed all of these things, why he had to come up with these ideas to start addressing and understanding why things in our solar system move the way that they do. What is causing the planets to orbit? How can we make sense of Galileo's experiments where everything falls at with acceleration, and that acceleration is independent of mass. It's the same value for every type of object that we drop. Okay. Now, let's take a look at the picture I have here. Here we have a planet. It could be a moon, could be an asteroid, could be an artificial structure. Let's just say it's planet Earth for now. And the planet Earth has a large amount of mass. Let's call that with a big M because it's the big one here. You're really curious about what the mass of the Earth is. It's 5.97 times 10 to the 24th kilograms. Yes, that's a lot of kilograms. So here we have the mass of the Earth. And let's just put what we call a test object, a test mass on the surface of the Earth. I'll imagine myself wearing this nice little hat, standing here on Earth. Gravity is going to be pulling me, trying to pull my mass and the Earth's mass together. The Earth has a whole lot of mass, so it's going to generate a whole lot of gravitational force acting on whatever mass we're going to put. So gravity is going to try to pull me down towards the center of the Earth, and here I am just being pulled down towards the center of the Earth. It'd be the same if you're over here. No, this person is not upside down. We define up and down by the direction that gravity is pulling us. Down is moving the direction gravity is pulling us. Up is away from the direction that gravity is pulling us. So in that sense, these are both upside right. Okay, so gravity is pulling us, keeping us on the surface of this round Earth. What is that force of gravity between this person here and the mass of the Earth? Well, Newton told us that. The force of gravity equals the gravitational equation. Big G, the product of the masses, divided by the distance squared. What would the distance here be? Well, we measure things from the center of the mass. So be the center of the Earth to the surface of the Earth where this person is standing. So it'd be the radius of the Earth in this case. If you're curious what the radius of the Earth is, it's about 6,400 kilometers. All right, So we know what the force of gravity is between this person and the mass of the Earth. And this is the genius. This is the beautiful insight. And this is why Newton spends so much time contemplating forces and motion. Because by Newton's second law, it doesn't matter what the force is, that force is going to equal mass times acceleration. That's Newton's second law of motion, that a force equals mass times acceleration. It is the force law. The amount of acceleration something experiences is related to the force. The bigger the force, the more acceleration divided by the mass. So go review Newton's second law if that seems a little bit mysterious. We said F equals ma. Here we're going to be talking about acceleration due to gravity. So we typically don't use a any longer as the variable. We use the lowercase g. So we have F equals ma. So F equals mg, using g as our acceleration. But we also have the force of gravity. That's the force that we're talking about. We have an equation for that. So we're going to set these two things equal to one another. By the way, you never have to do these kind of derivations in class. This is just for your edification. So setting those two equal to each other, we can cancel out the small m's. Notice that my mass doesn't matter. The mass of this ball is not going to matter, just like Galileo observed, to get that the acceleration due to gravity, this g, little g here, equals the universal gravitational constant times, in this case, the mass of the Earth divided by the radius of the Earth squared, or whatever mass you're talking about, whatever planet. We could put in the mass of the moon and the radius of the moon to figure out the surface gravity of the moon. We could put the mass of Jupiter and the radius of Jupiter to figure out the surface gravity of Jupiter. We could put the mass of the sun and the radius of the sun to figure out the surface gravity of the sun, the acceleration that we would experience if we were standing on the surfaces of those objects. For Earth, I can crunch all those numbers, crunch, 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 big G, but always make sure you put the units, then the mass of the Earth divided by the radius of the Earth squared. Notice, cancel out all the units, I do get meters per second squared in acceleration. And I can calculate that when I drop something, the acceleration on Earth is 9.8 meters per second squared. You can go measure that as well. So here we have a theory, Newton's gravity, and the second law of motion, predicting a value 9.8 meters per second squared. Then we could go do experiments. We could drop things, time how long it takes for them to fall, and use that to derive the acceleration due to Earth's gravity to get 9.8 meters per second squared. That's pretty cool that we can now have a theory that makes a prediction and do an experiment to actually prove or actually show that that prediction is correct. That's really, 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 really powerful. And also notice here that the mass of the thing on the surface doesn't matter. So it doesn't matter if I'm dropping a human, or if I'm dropping a ball, or if I'm dropping a wadded up piece of paper, or if I'm dropping a bowling ball. They all have the same acceleration, which is exactly what Galileo observed. It's like all these pieces are coming together. Holy cow, physics and science are really, 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 really powerful. It just has to take, we have to take a little bit of time to stop and absorb it and then contemplate what it all means and how it all fits together. Okay, this is the surface gravity of Earth. This acceleration of 9.8 meters per second squared is what we would call 1g. And you've probably heard people talk about G's before, like if you're talking about pilot simulations or pilot training for Air Force pilots, then they'll be put into simulations where in a tight turn, they might pull upwards of 2 to 3 G's. If you're launching yourself on a rocket and you're an astronaut on your way to the International Space Station, they might say during the launch, they're going to experience 2.3 G's. What they're talking about is how much acceleration they're going to experience compared to Earth, the acceleration we feel here on Earth. So how many 9.8 meters per second squared do we feel? 1g would be an acceleration of 9.8 meters per second squared, which allows us an easy way to start to play around with surface gravity. We can use the Earth surface gravity, 1g, 9.8 meters per second squared, as a standard. As long as we then put everything in relation to Earth, like how many times the mass of the Earth masses, how compare the radius to the radii of Earth radii, then all of a sudden we can start working with surface gravity and get answers pretty quickly and pretty easily. And that's what I'm trying to show right here. So we would have the surface gravity of some object, say the moon or Jupiter or the sun. And I could go ahead and write the equation for the surface gravity. I could write the equation for Earth's surface gravity. That's a bunch of numbers. That looks really, really, really confusing. But then I could look, and if I put the mass of this object in terms of the masses of Earth, so mass object divided by mass Earth, how many times more massive is it than the Earth, or how many times less massive is it than the Earth? What is its mass in Earth masses, and do the same for the radii, compare it to the radii of the Earth. The big G's cancel, and then I'm just left with the mass measured in Earth masses and the radius measured in Earth radii. I know that was a little bit of fancy mathematics right there, but now if we actually just use Earth masses, compare things to Earth and Earth radii, then we can get an answer what the acceleration of another object is and number of Earth surface gravities, number of G's. So we get all of this work to get a really simple equation that the surface gravity and number of G's, how many 9.8 meters per second squared, is equal to the mass and measured in Earth masses divided by the radius measured in Earth radii squared. Notice that this is an inverse square law. The surface gravity is directly proportional to the mass of the object and inversely proportional to the square of the radius of the object. Okay, I know we're doing a lot of work here. Let me actually show you some examples. Didn't want that slide in this, but sorry about that. So how might you experience working with this on the homework? And I'll only do very simple examples where I'll only change the mass or the radius and not both on exams. But I am going to eventually change both of them. So this first page, I'm only going to change either the mass of the object or the radius of the object. And you'd have to tell me how surface gravity would change in response. But then I want to show you some examples so you can see how powerful of a tool this is, and you can imagine what it would be like to be walking around on other planets. Okay, so I have some imaginary planet. Let's just call it Matera. It is 5 times more massive than the Earth, but the radius of the Earth is going to be the same. So I'm going to make this mass be 5 Earth masses, and I'm going to keep the radius the same, 1 Earth radius. So if I want to know what the surface gravity is for planet Matera, I could go ahead and calculate. I'd put the number of Earth masses on the top, 5 of them, the number of Earth radii on the bottom, 1 of them. 5 divided by 1 squared is just 5. So Matera would have a surface gravity of 5 G's, 5 times Earth gravity. So just shy of 50 meters per second squared. 49 meters per second squared would be the surface gravity of Matera, 5 times that of Earth. Which means that if you stood on a scale on this imaginary planet Matera, you would weigh, your weight that it would display would be 5 times greater. All right, let's do another imaginary planet. Imaginary planet Cetera has the same mass as the Earth, but now it's going to be twice the size. So it's going to get bigger, but have the same mass. So I have the mass is 1 Earth mass, the radius is 2 Earth radii. Let's just go ahead and use this equation up here. So the mass is 1 Earth mass, the radius is 2 Earth radii, square that. So the surface gravity on Cetera would be 1 divided by 2 squared, that's 1 divided by 4, 0.25, 1/4 Earth's gravity. That'd be 0.25 Earth gravity. Let me go ahead and calculate out what that number would be. That would be a surface gravity of 1/4 of Earth's surface gravity, which would be 2.45 meters per second squared, 9.8 divided by 4. Not that bad, right? Hopefully that's what you're starting to see. That's not too bad because I can square 2, and 1/4 is not that bad. Let me go to a few more examples. These are definitely not what I expect on exams, so don't expect this on exam 1 or the final exam. But I just want to show you that this can be used, this method can be used to answer some fun questions. Like, what's the surface gravity on the moon? What would your weight be on the moon? It's going to be less. How much less would you weigh on the moon? You still have the same mass, you just have a different weight. So all I have to do is know what the mass of the moon is in Earth masses. It's about 1.23% the mass of the Earth. So that would be an Earth mass of 0.0123 Earth masses. And I need to know the size of the moon. It's about 25% of the size of the Earth, 27.2% the size of the Earth. So it would have a radius of 0.272 Earth radii. Use that same process, so just go ahead and put the mass on the top, 0.0123. The radius and Earth radii on the bottom, 0.272. Square it, calculate that out, and you get 0.166 times Earth's gravitational acceleration, g's. So 0.166 times 9.8 meters per second squared. So the surface gravity on the moon is about 1/6 that of Earth's surface gravity, which means that if you were to go to the moon and stand on a scale, the number it would read would be 1/6 what it weighs here. So if you think about the astronauts moving around, they can really hop around. It's a different gravitational environment. And these kind of things, when we're designing spacecraft to go explore the moon, or these little helicopters that we're going to put on Mars and potentially on other planets as well, we need to know what the surface gravity is, because all of that is important to how those things will operate. And a pretty quick and easy way to do it. And let's just do one more. I've mentioned Jupiter several times. So the mass of Jupiter is about 320 times the mass of the Earth. The radius of Jupiter is a little over 11 times the radius of the Earth. So I could go ahead and plug those numbers in, put the mass on the top, 317.82 Earth masses, put the radius of Jupiter on the bottom, 11.21 Earth radii, square it, calculate that out. So if you could stand on the surface of Jupiter, what would the gravitational acceleration be if you could stand on a scale there? It would read 2.53 times greater than Earth's. So 2.5 G's would be the acceleration on the surface of Jupiter. So that's working with surface gravity. I'm going to hold off for orbital velocity and escape velocity for a second video, because I want these to be in separate, easy to contain chunks. So instead of doing one long video, I'm going to go ahead and split this up. And I will see you when we talk about orbital velocity. Notice that we're talking about things orbiting now. And we're going to be using our knowledge that Newton gave us to understand orbits. I will see you in that video.